Thank you very much for the introduction, and thank you to all of you for coming and listening. I guess in this workshop you probably all have heard of random polytopes and random geometric things, but you maybe haven't heard of extension complexity. And so let me start by introducing that concept. And so as a motivation, let's just start very easy. Let's look at. Get used to this thing. Okay. So let's just look at that regular hexagon. And as you can see, it has 6 facets, so 6 edges. And so that means if you describe this regular hexagon by linear inequalities, then you will need to write down 6 inequalities. Okay, but however, here's an observation. You can find a 3-dimensional polytope that only has 5 facets, so that can be described with 5 inequalities, which you can linearly project to this regular hexagon. So this picture indicates this. Here is a 3-dimensional polytope with only 5 facets, whose projection is a regular hexagon. So by going higher dimensionally, surprisingly, you were able to take fewer facets. And just as a remark, this construction only works for certain hexagons. For most hexagons, you can't do this. So there's something special about the regular hexagon and some other hexagons that you can do that. Okay, so here's again this observation. A regular hexagon can be obtained as the projection of a 3-dimensional polytope with only 5 facets, even though the hexagon itself has 6 facets. And so this now motivates the definition, which is written here. So the extension complexity of a polygon, or more generally of a d-dimensional polytope. Okay, so the extension complexity of a polygon, or more generally of a d-dimensional polytope, is the fewest number of facets needed to get that polygon or polytope as a projection. So more formally, the extension complexity of a d-dimensional polytope P is the minimum number of facets in a possibly higher dimension polytope P prime, so that one can obtain P as the image of P prime under linear projection. So P is given to you. P prime, you can choose whichever way you want, and your goal is to make P prime has as few facets as possible. And to do so, you can go to higher dimensions. So P lives in dimension D. In this picture, D is 2. And then in this picture, P prime would be in dimension 3, and you can go even higher. Okay, and so using this observation, just to finish this example, one can see that the extension complexity of a regular hexagon is 5. So this example shows that it's at most 5, and you can also check that you can't do better than 5. And more generally, the extension complexity of a 2-dimensional regular n-gon is on the order of log n. Okay, so here's again the definition. So hopefully it's clear sort of what the definition means. It's maybe not so clear why you would ever consider this. But so this study of this notion actually has a long history dating back around 30 years, motivated primarily by its relevance for combinatorial optimization problems. So I don't want to go into too much detail, but just to roughly describe why this is relevant, if you want to solve a combinatorial optimization problem by linear programming over some polytope, then the number of facets of the polytope, so the number of linear inequalities, are relevant at every step, and sort of the more they are, the slower your linear program will be. And so now if you find a higher dimensional polytope with fewer facets, so fewer inequalities projecting down to the original one, you can solve the programming, the linear program you wanted to solve on this downstairs polytope. You can lift that up to the upstairs polytope, solve it there potentially faster if there are much fewer inequalities, and so that gives rise to a much faster algorithm potentially. And so, obviously the additional dimensions may also slow it down, but then it depends on how many inequalities you save compared to the additional dimensions. In any case, people in combinatorial optimization study this notion of extension complexity. I mean, they've been studying it for a long time, and there's a lot of literature about it. So in particular, there's been a lot of work in the combinatorial optimization community on the extension complexity of specific polytopes, which are relevant in particular optimization problems. Like, for example, the correlation polytope, the traveling salesman polytope, and the perfect matching polytope. Don't worry if you don't know what these are, but I just want to indicate there's specific polytopes which are associated with specific combinatorial optimization problems. Where there's kind of, for each of these polytopes, there are long sequences of papers where they improve on the extension complexity bounds. In general, it's very difficult to determine the extension complexity of a given polytope. So that's already, I guess, shown by the fact that there's so much literature. So you can't just sort of look at the polytope and figure out what the extension complexity is. So it's a sort of, in some sense, fairly complicated notion. Okay, so here's again the definition. And so before we come to sort of the main topic of this talk, let me, which is the extension complexity of random polytopes, so coming back to the main theme of this workshop, let me give you some more simple general facts about extension complexity. So the extension complexity, because these are relevant in order to motivate the results later. So the extension complexity of a polytope is always at most the number of facets of the polytope, and also always at most the number of vertices. So that's the general upper bound. A general lower bound is that if P is a polytope with n vertices, the extension complexity is at least logarithmic in n, and also if it's a polytope with m facets, it's at least logarithmic in m. So it's sort of upper bounded by the number of facets or vertices, and lower bounded by the logs of these numbers. And for these previous points, you see how they're sort of symmetric in the number of vertices and the number of facets, and that's not a coincidence because the extension complexity of any polytope equals the extension complexity of its polar dual, which so that means it interchanges number of edges and vertices, facets and vertices, and so it's not surprising. These other general inequalities are they're symmetric in vertices and facets. And then the last point is that the extension complexity of a d-dimensional polytope is always at least d plus 1. Yeah, and so combining these facts, it's easy to see that the extension complexity of an n-1 dimensional n-vertex simplex is equal to n. So I guess I told you earlier, for most polytopes, it's very non-trivial to figure out what the extension complexity is. In this case, for a simplex at least, it's very easy. Okay, so here's again the definition. And so here's a natural extremer question. So my research background is mostly extremer combinatorics, so extremer and probabilistic combinatorics, and so asking extremer questions is sort of natural, but also this question has been studied in the combinatorial optimization community. Namely, what is the maximum possible extension complexity of a polytope with n vertices or with n facets? So as we saw earlier, it's symmetric to ask this question with respect to vertices or with respect to facets, so it doesn't make a big difference. So, so in other words, sort of if I know that the polytope has n vertices or n facets, how big could the extension complexity be? And for those of you who paid a lot of attention on the last slide, you might already see the answer. The answer is actually, this question is actually fairly easy. The answer is n, because an n-1 dimensional n-vertex simplex has extension complexity n. We also saw on the previous slide that the extension complexity is at most n if we have n vertices or n facets. Okay, so that question was boring. But note that this simplex is very, very high dimensional. So it's natural to ask this question also if we restrict the dimension of the polytope. So if a fixed dimension d, for example, d equals 2, and large n, what is then the maximum possible extension complexity of a d-dimensional polytope with n vertices? Okay, so here's again this question, and it's been widely believed for a long time that still the extension complexity could be as large as n, even if you restrict the dimension. So even if you force the dimension to be, say, 2, it was widely believed that the extension complexity could still be as large as n. But that was then roughly, I guess now it's exactly 10 years ago disproved. So Shitov and independently Padrol and Pfeiffer disproved this for d equals 2. So they proved that a two-dimensional n-gon has always extension complexity at most 6n/7, so it can't go all the way up to n. So restricting the dimension actually forces the extension complexity to be smaller. And so then this bound was improved to a little O of n shortly after, and a little bit later the bound was improved again by Shitov to a constant times n to the 2/3. So that means the extension complexity is actually quite a bit smaller than n. Okay, so these bounds were all for dimension 2. For any fixed dimension d bigger than 2, so even for d equals 3, no non-trivial upper bounds are known. So it's not even known that the extension complexity in dimension 3 is at most n minus 1. Yeah. Okay, so what about lower bounds? So here are the known lower bounds. So Fiorini, Rosbach, and Tivari proved that almost all n-gons, so again that's in dimension 2, have extension complexity at least on the order of square root n. So we know that's not true for all n-gons, like we saw that the regular n-gon has extension complexity on the order of log n, but almost all, so most n-gons have extension complexity at least square root n, and on the order of square root n, and so in particular that shows there exist n-gons which have extension complexity at least on the order of square root n. And so that was for dimension 2, and Padua proved a bit later more generally that almost all d-dimensional polytopes and n vertices have extension complexity at least on the order of square root dn. And I don't want to go in exactly into what the exact notion of almost all is, but basically the gist of these results is that if you pick a polytope randomly, you should have it shouldn't have too low extension complexity. So in other words, it seems plausible that random polytopes are good candidates for having high extension complexity. And so that then raises the question, so here again was this extreme question, but that now raises the question, what is actually the extension complexity of a random polytope? So these results on the previous slide gave some lower bounds for the typical extension complexity of, say, random polytopes, but maybe random polytopes typically even have even higher extension complexity. So that's a natural question, and in the sense that random polytopes are, I guess to everyone in this room, probably natural, and extension complexity might not be so natural to the people in this room, but very natural to the people in combinatorial optimization. And so these are both two sort of well-studied concepts. And so I think it's a natural question to ask what the typical extension complexity of a random polytope is. So let's say we fix a dimension d, what's the typical extension complexity of a random d-dimensional n-vertex polytopes? Now, of course, the question is what model of random polytopes do you take? And there are many interesting models. And I'm not claiming that the ones we considered are the most natural in this context. They were just the ones we happened to consider because they gave us the best angle of attack. But I think it would be very interesting to also study this question for other random polytope models. Okay, so in this work we considered two different models of random d-dimensional polytopes for fixed d. The first model is to choose n independent uniformly random points on the unit sphere in Rd and let the polytope be the convex hull. So in this model, the polytope has with probability 1 n vertices. The second model is maybe more common in probability theory, that you take m independent uniformly random points in the unit ball, so not necessarily on the boundary of the ball like in the first model, but m independent uniformly random points anywhere in the ball, and you let the polytope be the convex hull of these points. So now not all of these points are vertices of the polytope, but this model is very well studied, and already almost 20 years ago, someone who I believe is probably in this room figured out what the number of vertices typically is of this in this random polytope model. So for these m.
So by typically you mean the mean value or some other notion?
So asymptotically, almost truly. So with probability 1 minus little o of 1, the number of vertices will be a constant factor away from what's written here. So there will be within the constant factor of m to the d minus 1 over d plus 1. Okay. So here are now our results about these two random polytope models and their extension complexity. So we proved that for any fixed dimension d at least 2, if you take the first model, so you take P to be the convex hull of n, and I forgot to say this is joint work with Matthew Kwan, who at the time he and I were at Stanford, but now he is at IST Austria, and Yufei Zhao, who's at MIT. So P is the convex hull of these n random points on the unit sphere in Rd, so on the boundary of the unit ball, then in this first model, asymptotically almost truly, so with probability tending to 1, the extension complexity is within a constant factor of square root n. So that means that the lower bound of square root n for random polytopes that we saw on an earlier slide is actually the right number for random polytopes in this model. And then in the second model, actually the same thing happens. So if P is the convex hull of m random points in the unit ball in RD, and you let n to be this number here, I don't think I understand how this works. So you take this number m to the d minus 1 over d plus 1, and so as we saw, what's the relevance of this number? Well, it is the result from Matthias Reitzner on the last slide, that the number of vertices is typically on the order of n then, and so we proved that the extension complexity is typically on the order of square root n. So that means it's again on the order of the square root of the number of vertices. So in the upshot is, I mean, maybe the technical statement is a bit wrong. The upshot is, in both of the random models we considered, the extension complexity is typically on the order of the square root of the number of vertices. Okay, and so, as I said before, the lower bound in the second theorem is implied, I mean, the lower bounds are basic. So as I said before, the lower bounds are really not the new thing here. So the lower bound in the second theorem is implied by this result of Pato that we saw a few slides ago. And for both theorems, the lower bounds follow easily from the arguments of Fiorini, Rothfuss, and Chivari for their lower bounds. But the interesting part of our results are the upper bounds. So no upper bound, non-trivial upper bounds for random polytopes were known before. So basically what we prove is that for a random polytope, typically the extension complexity is at most the square root of the number of vertices up to constant factors. Okay, so here's again a summary of what we proved. So for both of these models, the extension complexity is typically roughly the square root of the number of vertices. And so a very natural open question is whether that's actually the extreme possible behavior. So coming back to this extremal question, which partly motivated this work, one can now ask, is it true that for a fixed dimension D and large n, is it always true that the extension complexity is at most a constant and square root n, where the constant may depend on D? As we saw earlier, for d equals 2, the best upper bound is a constant times n to the 2/3, and for larger d, no non-trivial upper bounds are known. So this is probably a very difficult question, but one could take the results for random polytopes at least as a heuristic that it could be plausible that such a bound holds. But of course, it doesn't tell you how you would ever prove such a bound. So that's basically what I just said. So it seems plausible that random polytopes exhibit the maximum possible extension complexity, but that's not at all clear. Maybe just as an intuition, why would you expect random polytopes to exhibit the maximum possible extension complexity? Well, heuristically, it's if you think back at the very first slide with this hexagon, it was a special property of some hexagons that there are projections of five facet polytopes, and most hexagons don't have that property. So it's sort of a special property to be a projection of something lower, something with few facets. And so if you pick something random, then it will be plausible to assume that you don't hit that special set, and so that random polytopes would have maximum possible or close to maximum possible extension complexity. But yeah, again, that's just a heuristic. Okay, so here's again this question, whether the square root n behavior is sort of the extreme possible. But because this question is very difficult, I think it's also natural to ask this question for special classes of polytopes. So for example, polytopes with all vertices on a sphere. So even then, it's not known whether every d-dimensional n-vertex polytope with all vertices on a common sphere has extension complexity at most constant times square root n. But we proved that the answer is yes for d equals 2. So I won't say so much about this in this talk, because this talk is mostly about the random results. But with similar methods, we also got results for all two-dimensional n-gons with all vertices on a common circle. That the extension complexity is then at most 24 square root n. So that was following sort of similar ideas. But unfortunately, we couldn't make that work in higher dimension. Okay. So that was again this result. And this bound is actually also tied up to the constant factor 24. Up to the constant factor here. So here's a picture illustrating this. If you have n vertices on the sphere, then this gives an upper bound that the extension complexity is at most a constant times square root n, and square root n is also the right behavior. As you can see, for example, by looking at the result in the first random model, where you took the n random points on the sphere and their convex hull, yes, our result showed that typically the extension complexity is at least on the order of square root n. So there, this intuition that random polytopes seem to be exhibiting the right behavior seems correct. Okay, so as I said, the proof for this result for non-random two-dimensional polygons with all vertices on a sphere follows a similar strategy as for the results on random polytopes. But in this talk, I want to mostly focus on the random polytopes. But before I do that, let me say one more remark about other things you can ask. So finally, you can ask what happens if you let the dimension d grow slowly with n, because in our results d was fixed and n was large. So one can show that in some sense you can then get polytope with relatively low dimension whose extension complexity is still in some sense close to n. So more precisely, we showed that for any n there exists a polytope with at most n vertices, dimension at most n to the little of 1, and extension complexity at least n to the 1 minus little of 1. But of course, I mean, there's still a little of 1 terms everywhere. So, but it just shows that you have to be careful sort of how fast you let the dimension grow with n. But if you are careful about this, I think it's certainly interesting to study also random polytopes in this regime where the dimension grows slowly with n. So you can ask about the extension complexity of a random n-vertex polytope where the dimension d grows slowly with n, or you can also ask, so that's a question at the bottom, or in the middle you can ask this sort of extreme question in this regime. But as I said today, I want to focus mostly on these results for random polytopes. And so for the remainder of the talk, so I guess that's sort of the second half of the talk roughly, I want to give you an overview of the proof of these random polytope results, because I guess stating the results is maybe interesting, maybe not, but I think it's sort of also interesting to see a little bit what the proof approach was. And of course I won't go through the proof in all details, but I just want to give you an overview. But in order to do that, I first need to take a little detour and tell you about non-negative rank because of matrices, because that is a concept which is sort of very crucial use in the proof, so I won't be able to say anything about the proof if I don't tell you about this. Okay, so extension complexity is closely connected to this notion of non-negative rank. And so here is in a top box the definition of a rank of a matrix. You all know this definition, but I just wrote it down in a particular way, which is not the way you would usually write it, but that's just to motivate the other definition. So a way to define the rank of an m by n matrix, and that's equivalent to the normal way you would define it. So the rank of an m by n matrix over the reals is the minimum number r, so that there is a factorization of m as t times u for some m by r matrix T and an r by n matrix U. So maybe you've seen that as a linear algebra, maybe you've put that as a linear algebra exercise on your students' homework sheets or something, or seen that in some other context. It's not how you would usually define rank, but it is, you can check, or make your students check on the homework. It's equivalent to the standard definition of rank. Okay, but so now let's take that and define non-negative rank by forcing everything in this definition to be non-negative. So the non-negative rank of a non-negative m by n matrix, so defining non-negative rank only makes sense if the matrix in the first place is non-negative. So you take an m by n matrix where all entries are non-negative real numbers, and then the non-negative rank is the minimum number r, so that there's again a factorization of m as t times u on a non-negative m by r matrix and a non-negative r by n matrix. So it's the same as above, except that you force the matrices T and U to have non-negative entries. And so then you can check that the non-negative rank, because this is sort of a more restrictive class of factorizations allowed, the non-negative rank is at least the ordinary rank, but it could a priori be much larger. And you can write down examples where the non-negative rank is significantly larger than the ordinary rank. Okay. So now let me connect this to extension complexity. And so this connection was known, I guess there will be a year probably on the theorem in a moment, but I mean that was known sort of 30 years ago. So that's a very classical connection. So given a polytope P, we can describe P by a list of linear constraints, so linear inequalities, which correspond to the facets of P. So each of these constraints will have, so I would really like to point at this, but I don't think
it works. Look, it works. Look at the look to the slides. Look to the screen.
No, you
look there. Try it.
yeah. So every constraint will have such a form. So it will be some linear inequality given by the vector A and the number B, and then the linear inequality has the form that A dot product X is at most B. So every linear constraint has this form. And so now if you have a vertex V of the polytope, then the slack of that vertex with respect to that constraint is basically how much slack do you have in this inequality. So how much space does the inequality have with being true. Since V is a vertex of the polytope, you definitely know that it satisfies the inequality. So A dot V will be at most B, and the slack is now the difference, which is non-negative. So B minus A times V, which says how much space do you have in inequality being true. Okay, so that defines what, so you have this polytope. For every facet you choose such a, so for every facet you have a constraint, you choose an inequality. I mean, up to renormalization, the inequality is unique, describing that constraint. And then for every vertex you calculate the slack with respect to every constraint. So now it's very natural to arrange these numbers you get when you calculate this in a matrix. So the slack matrix of a polytope P is the non-negative matrix where all the slacks are the entries, so the rows are indexed by the vertices and the columns are indexed by the constraints, and then for every vertex you look how much slack there is in the constraint, and because the slack is always a non-negative number, you get a non-negative matrix. Okay, and so now you might wonder why would you do that, but the reason you do this, first one comment, so you can think of the slack matrix of P as the matrix recording the slacks, but you can also, if you don't like these slacks and you find it confusing, you can think of it as the matrix recording the distances of the vertices from the hyperplanes to the facets. Because up to renormalization, you can choose these linear inequalities as just measuring the distance to the hyperplane to the facet. So if you don't like the slack version, this inequality version, just say, well, you take a matrix where the rows are the vertices of the polytope, the columns are the facets, and now for every vertex and every facet, you look at the distance of the vertex from the hyperplane to the facet. And that's some number, and all these numbers you record in this matrix. And so now here is the connection to extension complexity. So if you look at that matrix and look at its non-negative rank, that non-negative rank is exactly equal to the extension complexity of the polytope. So that was proved by Yanakakis now 33 years ago. So that's a very old connection. Okay, but so that now motivates why non-negative rank is important here, because you can now study the extension complexity of a polytope by studying the non-negative rank of its slack matrix. And so in order to prove our desired upper bounds for the extension complexity for these random polytopes, what we actually do is we bound the non-negative rank of these slack matrices of the polytopes. Okay, so so let me now give an overview of how we actually do this. Okay, so here's again our theorems. So the first one is about the convex hull, is the first random polytope model, so the convex hull of n random points on the unit sphere. And so then we want to show that the extension complexity is, I guess the main point is the upper bound, so we want to show the extension complexity is at most a constant times, is typically or asymptotically almost fully at most a constant times square root n. And then the second model, you had these m random points in the unit ball and take the convex hull, and then you had this upper bound. You had this upper bound, which was in terms of this number n here. So in terms of this number n there, which was closely related to the number of vertices of the polytope. Okay, so so as I said, in the first theorem, all vertices are in the unit sphere. In the second theorem, the vertices are not on the sphere because it's a convex hull of these random points in the ball. But typically in this model, the vertices are close to the unit sphere. Because if a random point is closer to the center of the ball, then it's unlikely to be a vertex of this random polytope, because it's very likely to be contained in the convex hull of other points. And so in both cases, the vertices of P are fairly well distributed on or close to the unit sphere, and that is just to motivate why the proofs of those two theorems are actually very similar to each other, because in one case you're exactly in the sphere, in the other case you are sort of close to it. And so for simplicity, in this proof overview, I'll only focus on the first model. The second model is a little bit more difficult in terms of studying the random distribution of the vertices, because I guess it's a bit more complicated. I mean, they're not uniformly random anymore as in the first model. But in terms of the ideas for bounding the extension complexity, it's the same. So let's focus on the simpler case with the first model. Okay. So, so here we fixed now this dimension D, and we want to upper bound the extension complexity of the polytope obtained by taking n uniformly random points on the unit sphere in RD. Okay, so here is first some general observations about what happens with the extension complexity, or more generally with the more generally speaking, we want to study the non-negative rank of the slack matrix, and so we'll study certain submatrices. And so on this slide, there will be some considerations of what happens if you take any d-dimensional polytope with vertices on or close to the unit sphere. So on this slide, it doesn't have to be random, but later we'll apply that to our random polytopes. Okay, so V is the set of vertices of P, and F is the set of facets of P. So again, P is has let's say vertices on the unit sphere in RD, where D is fixed. And so now M is the slack matrix of P, so that means the rows are indexed by these vertices B, the columns are indexed by these facets F. And so then every entry you could say counts the slack, or if you don't like that, you can say every entry is the distance of the vertex from the facet hyperplane. Okay, and so the following is a key lemma for our argument, and it's inspired by a similar lemma due to Sheetov. And basically what this, a similar lemma due to Sheetov specifically for the two-dimensional case. And basically what this lemma does, so overall, remember we want to upper bound the extension complexity. So that means we want to upper bound the non-negative rank of the slack matrix. And so what this lemma does, it is to upper bound the non-negative rank of a certain submatrix of the slack matrix. Okay, so what this says here is that F prime be a small patch of facets of P. So now I'm of course very vague of what I mean by that, and we can discuss in more detail later, but I didn't want to get too technical. So just imagine a little piece of the unit sphere, and so take the facets with the vertices which are roughly there or close to there. So just, if you take the thing of the polytope as a soccer ball, it's a little patch on the outside of the soccer ball. Okay, so you take a small patch of facets of P, and now you take a subset of the vertices which are far away from this patch, so which are far away from the facets in F. So that's V prime, and F prime is a patch of facets. And so now let's look at the submatrix of the slack matrix with the vertices in V prime and the facets in F prime. And so that's some submatrix of the slack matrix. And what this lemma says is that the non-negative rank of the submatrix is overformed. So it's bounded by some constant only depending on D and not on anything else. Okay, so Sheetov's version of this lemma was only for dimension 2, and it does not require this far away assumption. So in Sheetov's version, the vertices just needed to be outside of this patch. For D larger than 2, you need this assumption, and the proof of this lemma is geometrically much more involved. So let me maybe give you a brief overview, because it sounds now like, otherwise it sounds a bit like cheating. I'm telling you I want to upper bound the non-negative rank of some big matrix, now I'm telling you where certain parts of it have bounded. Let me at least give an indication of why that is. And it's easiest to first explain the idea in the two-dimensional case. So that's this lemma of Sheetov. So in this case, it's a two-dimensional polytope, and M is its slack matrix. So now, what is a patch of facets? In this case, it's just a sequence of consecutive edges. So you take some part of the boundary of the polytope consisting of consecutive edges, and now you take V prime to be the set of vertices which are not on those facets, so the ones outside this sequence of consecutive edges. And so now what this lemma says is that the non-negative rank of the submatrix of the slack matrix corresponding to V prime and F prime is at most 4. So in this case, the constant is 4. And so here is a geometric picture trying to explain this. So here is V prime, it's some set of consecutive facets. This is F prime, here's V prime, these are the vertices outside that patch. So black vertices are V prime, the black facets, so the black edges are F prime. And so now we want to prove that the submatrix with rows corresponding to V prime and columns corresponding to F prime has non-negative rank at most 4. So here's the proof idea. So V prime is some sequence of edges. So you take the two outermost ones and extend them, like in this picture. Then all these vertices in V prime sort of lie between those two rays. Let's now take 4 orange points, namely that vertex, and let's take those very far away on those two rays, so that the convex hull of these 4 points contains all vertices in V prime. So that's possible just by pulling those far enough so that it contains everything. Okay, so now the vector of slacks, or distances if you like, of each vertex V in V prime with respect to the facets in F prime is now a convex combination of the respective vectors for the 4 orange points. So for example, if for this point, this point is some convex combination of the 4 orange points. If I now want to calculate the slack of this point with respect to, say, that facet up there, I can take the corresponding slacks of the corresponding slacks I would get for those 4 orange points, and then again take the same type of linear combination. Because everything is linear, it behaves well with respect to linear combinations, convex combinations. So that means for all of those points, I can get their vectors of slacks with respect to the facets in F prime, just as convex combinations of the 4 corresponding vectors for the orange points. But those vectors for the orange points are non-negative vectors, so that means in this matrix MV prime F prime, every row is a linear combination of those particular 4 non-negative vectors. And so that shows, so every row of MV prime F prime is a convex combination of these 4 non-negative vectors corresponding to the 4 orange points. And so that means that that matrix has non-negative rank at most 4, because I found such a factorization. Okay, so that's the proof in dimension 2. Now in higher dimension it gets a little bit more complicated, but the idea is the same. So the idea is still the same, except that it's not so clear anymore what to do for these 4 orange points. Because you can't just take the outermost facets and extend them, because that may actually lead to a lot of vertices. Right? Because there's no bound on the number of facets here, and also not at the number of facets at the, say, outermost boundary of that patch. And so I can't just take the outermost ones and extend them. So a slightly different approach is needed, and that's also related to the fact that you need this far away assumption. So you can, so in this case now the vertices in V prime, the black dots in this picture, don't have to be just outside this yellow patch of facets, but they have to be quite some, a little bit of a distance away, like indicated in this picture. Okay, but the rough idea is the same. So the orange, the 4 orange points in the convex hull, and the proof will be replaced by some polyhedral lampshade polytope. So what do we mean by that? Something looking like a lampshade, like in this picture. But the important thing is that this thing should have O of 1 vertices. So the number of vertices should only depend on D and not on V prime or F prime or any of that. But yeah, so if you are very careful with how you construct this, you can get such a polyhedral lampshade polytope with O of 1 vertices, which contains all these black dots in V prime, and which lies entirely on the positive slack side of our facets in F prime. Right? Because it was important earlier that the orange vectors, their slacks were non-negative, so we need this entire lampshade polytope to lie sort of under all facets. So if you, in this picture, take any facet and take its hyperplane, the whole lampshade should lie below that hyperplane. So yeah, but if you're careful, you can construct such a polytope, and then, I mean, it's a little cumbersome, but it's not sort of, there's not real difficulty, it's just cumbersome with the geometry. Okay, So, so then the argument after you have this lampshade polytope is the same as before. So every vertex v in v prime is now a convex combination of the vertices of this lampshade, right? Because the lampshade contains our black dots in v prime. And so that means the vector of slacks of every vertex v in v prime, so every black dot up there, is a convex combination of the slack vectors of the vertices of that lampshade. And these are O of 1 non-negative vectors. And so that tells us that the non-negative rank of this matrix MV prime F prime is O of 1. Okay. So, as I said, I omitted a lot of details, but hopefully I roughly convinced you that for submatrices of that form, we can bound the non-negative rank. But of course, now is still the question, how are we going to use this to bound the non-negative rank of the whole matrix? So let's remember our setup. So we had some fixed d at least 2. We had P, which was a d-dimensional random polytope with n vertices obtained as the convex hull of n independent random points on the unit sphere. So that was our first model. As I said, the second model, the argument is similar. For simplicity, I stick to the first. So d is fixed, n is very large with respect to t. You take n uniformly random points on the unit sphere in Rd and take the convex hull, that's your random polytope. And so now, typically the vertices of P are well distributed over the sphere, and the facets of P are fairly small. So obviously I'm being very vague of what that means, but basically, I guess in this room, it's probably natural to everyone that if you, I mean, I've given this type of talk also with combinatorial optimization people. For them, it was very natural what extension complexity is, and maybe less natural how a random polytope looks like. Here, it's probably the opposite. So as you can all imagine, the vertices are not very clumped together anywhere typically. Okay, so now here's the approach. So we cover the sphere by on the order of square root n small caps. So small spherical caps, so that each facet of P is inside one of the caps, but each cap contains only on the order of square root n vertices. So obviously we can't always do this, but we can asymptotically almost surely do this. Now, of course, I also mean, depends on what I mean by small, but you can choose the parameters appropriately that you can typically do this for a random choice of the points of a random polytope with this model. Okay, so now you have these small caps. And these small caps now give the patches to which you apply this lemma on the previous slide. So the sphere is covered by these small spherical caps, which also overlap a little bit, so that each facet nicely lies inside one cap, and no cap is too crowded with having too many vertices. And now each of these caps gives you a patch of facets to which we want to apply the lemma on the previous slide. So that means we can partition the slack matrix into parts, where by the lemma, most parts have small non-negative rank. So what I mean by that is, well, the vertices lie in some caps, the facets lie in some caps, and so on. And so the lemma on the previous slide always tells us if you look at some patch of facets and omit the vertices which are inside that patch or close to it, then for all the remaining vertices, we have that's sort of subset of the columns. So if you now delete sort of the vertices which are close to that patch, then for the remaining rows, which are most of the rows, that subset of columns has small non-negative rank. So it's believable that you could try to bound the non-negative rank of the whole matrix by that. But one crucial question is, what do you do with the entries where the vertex is actually inside the same patch as the facet? Right, because the lemma on the previous slide was talking about vertices being far away from the patches. And so this will never give us a handle on the sort of diagonal blocks of that matrix, so the vertices which are inside the same small cap as the facet. So that's the challenge. So the challenge is to deal with the stacks of vertices with respect to the nearby facets. And so to handle this, I actually lied to you. The lemma on the previous slide was not enough. We need a stronger version of this lemma on the previous slide, which is more technical. That's why I didn't tell you the full statement. But we need a more technical version of the lemma on the previous slide, which allows you to make certain subtractions from the matrix. And so basically that lemma, I mean, it's a bit technical, so that's why I don't want to state it in full, but basically it says like, you have again this patch of facets, these vertices which are far away, and now it just doesn't just say something about the non-negative rank of the matrix MV prime F prime itself, but also the non-negative rank when certain types of subtractions are allowed from that matrix. And so these subtractions correspond to subtracting rows which correspond to slacks of vertices inside that patch from the rows with respect to the V prime vertices. And so with a stronger, more technical version of the lemma, we can then deal with these sort of diagonal type entries, so these entries of vertices with respect to nearby facets, which are in the same small cap or otherwise close to each other. So we can deal with that by sort of basically zeroing out these entries very carefully with subtractions, which are still allowed with respect to the technical version of the lemma with the subtractions. But since this is rather technical, I don't want to bore you with the details. Roughly the strategy is what I explained, but one has to be more careful to deal with these sort of diagonal blocks of that matrix. Okay, so that's all I wanted to say, and thank you for your attention.